Hello and welcome to another LeetCode video. Today we're going to be working on kth largest element in an array. It's a really common interview problem, and I'm going to show you a bunch of different ways you can solve this, along with the pros and cons of each of them. So let's get started. So first of all, obviously, like in this problem, you are asked to get the kth largest element, and they ask you to get it without sorting. So let's just actually really quickly, briefly mention how we would do it with sorting. So if we sorted, it would be pretty straightforward. Let's say we had these numbers, we would sort. So we'd have like 1, 2, 3, 4, 5, 6. And if we're asked to get the kth largest number, that's essentially, so if this is 6 elements, the kth largest is 6 minus k. And let's think about that and let's figure that out. So if k is 2, then we would get 4 here. So this is 0, 1, 2, 3, 4. And this is the kth largest number. This is the second largest number. So if k was 1, you would go here. If k is 2, you'd go here. If k was 3, you'd go here, and so on. And so that's a really easy way to do it with sorting. Now, I would imagine that in a coding interview, they're probably not going to want that solution because that's a little bit too easy, right? Just sorting and getting the kth largest that way. So let's go through it a few more ways. And another way to do it that's really common is using a heap. And so what a heap does is, in Python at least, you have a min heap, and it is essentially a semi-sorted array of numbers that will give you the smallest number possible, right? So the heap will not be completely sorted, but it'll be somewhat sorted, and essentially a min heap, it's technically stored as an array, but it's supposed to represent like a tree where every parent node is bigger than all, or smaller than all the child nodes for a min heap. So like this node would be whatever, and then it would be smaller than these two nodes, and then these two nodes would be smaller. Like each parent is smaller than the children. You're guaranteed of that. But you don't necessarily have a completely sorted heap. You just know that like the first element is going to be the smallest element, and then the rest of it will have some kind of structure, but it's not going to be completely sorted. And a heap has a few operations. It has heap push, which will add an element onto the heap and maintain its semi-sorted order. And this is a log n operation, where n is the size of the heap. Then we also have heap pop, where you get rid of the smallest element in the heap and maintain the semi-sorted order, where the first element in the heap would now be the smallest element. This is also log n, where n is the length of the heap. And we have heapify, that transforms an array into a heap, and that is an order n operation. And then finally we have, I think it's like, actually in Python you could actually just get an index directly. So if you just get the element at heap 0, this will give you the smallest element, and this is obviously O of 1. So these are the operations that you're most likely going to use for a heap. There is other stuff. There is actually literally a thing that will give you like the kth largest element, I'm pretty sure, in a heap, or the k largest element. So there is a way to do this in like a one-liner in Python, but that's probably also something I don't know if people would be looking for. But there's a few ways to do this, and let's talk about the different ways. So in Python, you have a min heap. So one of the ways you could do this was you could transform nums into a min heap. And so let's do that. And we're going to write this sorted, but it's not actually going to be sorted in Python. But essentially, if you transform it into a min heap, every time you pop, you will get the smallest number. And so we can just figure out like how many times we need to pop to get the kth largest number, and it wouldn't be that bad, right? So like if the number was here, if this is k equals 2, we'd need to pop how many times? 1, 2, 3, 4, 5 times. So you could just figure that out using the length of the array and k to figure out, like, I'm not going to do that here, but you can literally just figure out like how many times you have to pop out for a given k given the length of an array. And we're just going to go through the space and time complexity of that solution, right? Where you just take the array, you turn it into a heap, and then you just pop sometimes to get that from the min heap. And that would totally be fine. So with that, assuming we don't use nums in place, that's going to be O of n space. And it's going to be, we're going to have to pop like roughly n minus k times, not exactly. It's going to be like n minus k plus 1 or something along those lines. So that's going to be the time, and k can be n, so this can technically be worst case O of n. And that's kind of the thing I'm trying to show is usually like the number of pops you have to make are going to be roughly O of n no matter what you do. And also for every single pop, that's going to be log of your actual data structure. So it's actually going to be n log n, worst case, right? Like if k is like 1 or something, that means you're over here, you'd have to pop this entire thing. So that's one way to do it. So that's going to be roughly n log n worst case. Average case, let's just say, you know, that would be something like, this would still be O of n, and let's say k is somewhere in the middle, you would get something like O of, it would still be n log n technically if k was in the middle, but once k was a little bit better, then it would be better, right? Because this would always be this, but technically, you know, best case scenario, this would be like 1, and then you'd have log n, something like that. So that's one way you could do it. Now another way you could do it is, what you could do is, instead of storing it like this, you could take every number and make it negative. And now, if you think about it, every time you do a pop, you'll get the biggest number. And so now it's a little bit like the calculation to get k is a little bit more straightforward. You have to pop just k times, right? So if k is 2, you have to pop like twice. Because for a min heap, you would get the smallest element, which would actually be the biggest element if you just make everything negative. And that would also be kind of the same, because imagine k is over here, then you'd also have to pop roughly n times. And so that would also be n log n. It's just another way to do it, and O of n space. So those are the two ways to do it. If you just heapify, if you just heapify your stuff, and you can either transform it into negative or not. Now, kind of like a clever-ish way of doing it, but it's also going to be roughly the same. It's going to be a little bit better space-wise for small k's. Like, let's say n is, you know, like 10 to the 5th and k is small, then it's going to be a little bit better. And so what you could do is you can make a min heap of size k. So size k. And let's just put in like the first k elements of this array. So let's look at that. So let's say we have 3, 2, 1, 5, 6, 4. So what you could do is you could just say like, okay, give me these first 3 elements. I'm gonna make a heap out of those, and so I'm gonna draw them. So like I said, it's a semi-sorted heap. Is semi-sorted. It's not completely sorted, so it's not actually gonna look like this. I'm just doing this for visual representation. So like the first element you're gonna pop is gonna be this one. The second element is gonna be this one, and so on. But it's not actually completely sorted. Okay, and then all you do is every time you go to the next element, you just check, is my element bigger than the min, right? So the min is in this case. Let's actually go through how that algorithm would work. So, and this is like probably like what a medium problem might be looking for. It's a little bit trickier, but you know, nothing too hard. So we were going to start over here because we looked at the first 3. We're going to say, okay, is 5 bigger than the min of the heap? And we have easy access to the min of the heap, right? That just heap 0 for a min heap. So 5 is bigger than the 1. So we're actually going to, if 5 is bigger, we want our heap to contain the k biggest elements at the end, right? So if k is, actually, let's go back a little bit and let's actually change this. So because in this example k equals 2, so let's actually take the first 2 elements only. Okay, so we're gonna have 3, 2. Now we are at this 1. Okay, and we're gonna say, okay, is 1 bigger than the min of the heap? So the min of the heap is 2, which we have access to. No, it's not. So we don't really care because we want our heap ideally to have the 2 biggest numbers at the end. That's why we made it of size k. Okay, what about 5? Is 5 bigger than the min? Yes, it is. So we're actually gonna get rid of the min with a heap pop, and then we're going to put in the 5. Okay, now for the 6. Is 6 bigger than the smallest element in the heap? Yes, it is. So we're going to get rid of the 3, and we are going to put in the 6. Okay, and what about the 4? Is 4 bigger than the smallest element in the heap? Well, no, it's not. So this is our heap at the end, and now if you think about it, heap 0 should always contain your kth biggest value, because if you have a heap of length k, where k is the biggest k elements, using our min heap, then the min of that is the kth element, right? So if you have like 5 elements, like 1, 2, 3, 4, 5, the minimum one of that is going to be the 5th largest element. So that's how you do the min heap, where you just go through your numbers. And let's think of the time and space complexity for that one. So let's say we're not doing this in place. Our space would be O of k now. So if k is a lot less than n, we're actually saving space. But keep in mind, k can be n as well. So worst case, it's still going to be O of n. So this is just roughly like how many different ways can you do a problem and like what's a little bit better. And what's our time? So if you think about it, we don't necessarily have to change our heap, but worst case, we would have to do also O of n heap pushes and heap pops, right? Because like if we just had a sorted array originally, our number would always be bigger. So if we just had like this, 4, 5, and so on, and we had whatever heap, anytime we get to a number, it's always going to be bigger than the min. So we're going to have to do a heap push and a heap pop. And so a heap push and a heap pop costs log n. So we're going to have log n, and then it's still going to be n because the length of the array is n. But this is a little bit better, right? So we have n log n just like last time, but we have now O of k space, so we're saving a little bit, which is pretty good. And so now we're going to go through the last solution, which is the quick select solution. So let's actually delete this stuff. But yeah, I would say for the medium part of the problem, a quick select is really rare. It's not super hard to do, I'll go over it, but I'd say something like a min heap of length k is somewhere along the lines of a medium problem. Obviously sort would be like an easy problem. They'd probably ask you to do something trickier than that, but let's go over quick select. Okay, so essentially in quick select, what's going to end up happening is it's kind of like a quick sort, where we're going to go through this example here, actually. So what we're going to do is we are going to have our array, and you can either do this in place, or you could, there's a bunch of ways you could do it. You could do it in place, you can make you can copy this if you want to like preserve this, right? You can just copy it into another array. You can do whatever you want. Like that part doesn't really matter. So, so you can ask like, can I modify the inputs? Can I not? Whatever. Okay, so essentially what's going to happen is we're going to have a left and a right index, kind of like in a binary search. They're going to start at the end. And then we're going to pick a pivot point. And the way it's recommended to pick a pivot point is not to pick, so you can technically pick any number in here, but if you always just pick the last point, then if your array is initially sorted, you're going to have O of n squared. So the way it's recommended to pick a pivot point is actually randomize a number in here. So just say like, I'll just pick a random number. And so we're actually going to do that. So let's just say we randomly get this 5. So then what you'd want to do is you'd want to swap your 5 and your last element, because that's still going to make it easier for your writing operation. So we're going to swap this and this, and we are going to put in a 4 over here and a 5 over here. So our pivot point is this 5 that we picked. We just swapped to make it easier. Okay, and now essentially what we do is we just start. This is like that problem that you're writing ones into the first available slot type of situation. So let's take a look at what that looks like. So essentially you have a write to index, and every number that's less than 5, you're going to write to your index. You're actually going to swap your numbers. And then once you're done, you're going to put the 5 in there. So let me show you what that's going to look like. So let's say we're at this index. 3 is less than 5. So we're actually going to swap the 3 with this index. So we have like 2 indices, I guess, one that we're writing to and one that we're writing from. So let's call this top one the one that we are writing from. And this bottom one is 2. So let's just call that 2, and let's call that maybe from or something. Let's just remember that. Okay. So right now they're both pointing to the same place, so you're just swapping a number with itself. So then this one always gets updated, and this one only gets updated if you write to something, right? So now they both get updated. Now 2 is less than 5, so it's the same thing. It's just going to write to itself. So they both get updated. 1 is less than 5. Cool. Now they're both going to be over here. 4 is less than 5 as well. And now finally 6 is not less than 5. So if 6 is not less than 5, we're essentially done. We've checked everything, but our write to is still the 6 because we didn't write to it. Now, once you've checked every single number, what you're going to do is you're going to say, I know that like all this is less than 5 because I wrote to it, but this number, wherever my index is at, that number is greater than 5. And you want your like array to be in the format of like less than, and then your pivot point, and then greater than, right? So that's what you want, and we're close to that. But right now we have a less than, and then our pivot point's actually at the end. So what we're going to do is we're going to swap wherever our pivot point is with our number. So let's do that. Let's swap our 5 and our 6 here. Okay, so let's put our 5 here, and let's put our 6 here. And so what do we know from doing this? We know for sure that because everything that's less than or equal to 5 is over here, it has to be, right? That was what we did. And everything greater or equal to 5 is over, or it's only greater than 5 is over here. So these numbers don't have to be sorted. As you can see, they're not, and these numbers don't have to be sorted. But we know that the index of 5 is exactly where 5 would be in a sorted array. And so now our k was 2, and we would just say like, okay, well, for k being 2, so this actually worked out really well. But let's just so for k, if k was 2, then our pivot point lines up exactly with the k, right? K equals 2 would be here in a sorted array. So we would actually return 5 here, but let's say k is not 2 because that would like kind of make it a little bit too easy. Let's say k is 3 or something. Okay, so if k is 3, that means the value needs to be over here. And we know all of these numbers are less than 5. Like, we know that for sure. And our number needs to be over here. So what part of the array can we get rid of? Well, if we know everything here is less than 5, or equal to 5, and we know our answer is obviously less than or equal to 5 because 5 is here, so everything, like our answer has to be less than or equal to 5, and it has to be in here somewhere, right? So that means we can get rid of all of this, and we can update our right pointer now to be over here. And similarly, you know, if k was 1, then the element would have to be over here, and then we know our number would have to be greater than 5, and yeah, I mean, I guess like technically if there's only one value past the pivot, you know it's there, but you're not always going to have that. So essentially we can get rid of half of our array on average case, right? Worst case scenario, it's going to be bad, but on average, let's say our pivot's always somewhere in the middle, we're getting rid of half of our array at every single time. So now we update this R, and let's actually write down this array one more time down here to see like what we have left. Okay, so we got rid of this whole section. We don't really care about that. So now this is our array. And our k needs to be here, right? We know that. This is where our k needs to be. So technically, you do have a right side still with a 5 and a 6, but we don't really need to use that anymore. And we know our k equals 3. So the element we care about is here, but as you can see, this is not sorted. Like, yes, 4 is the number we're looking for, but this could easily be in any order because this is just numbers less than 5. So it could easily be, you know, 1, 2, 3, 4, 3, 2, 1, 4, 4, 3, 1, 2, whatever. Okay, so now we're going to pick a random index again, right? So, and like I said, the reason you pick a random index as opposed to picking the last index, and I learned that from I actually submitted this by always picking the last index, and it was a lot worse of a runtime than just like a suboptimal solution. And that's because if you think about it, if you're working with data, a lot of times your data will be completely sorted or close to sorted or like in reverse. So picking the last index or the first index will give you like the worst case complexity quite often. That's why picking a random index, like there's a very low chance your data is just like sorted in some random way that happens to match the way you're finding your index. But if you just pick the last one in a sorted array, that would be n squared time complexity. So that's why you want to pick a random index. So let's just say we pick this index over here. Okay, well, we're going to swap these two, right, just to make it easier for ourselves. So we're going to swap this 4 and this 2. Okay. Now, this is going to be our pivot index. And we're going to have the same kind of thing where we're writing from and we're writing to. So remember, the top is the right from and the bottom is right to. Okay, so is 3 less than 2? Well, obviously it's not. So our right to is still going to be the same because we haven't done anything, but our right from is going to move. Okay, is 4 less than 2? No, it's not. Is 1 less than 2? Yes, it is. So now we have to swap whatever we're writing from and whatever we're writing to. So this 1 and this 3 need to swap. Okay, so we're going to write the 3 here and the 1 here. And now we are done, but we also need to update our right to index. Right? We wrote to here, we need to write to the next one. Okay, so our right to index is over here. Now remember, for our pivot we know for sure has to go here because everything here or later is greater than the pivot, otherwise we would have written to it, right? Like this is the index of numbers we haven't written to yet, so everything to the left of it is numbers less than it. So we're going to need to swap this 2 and this 4. So let's do that. So we're going to swap the 2 and the 4. And there we go. Okay. And now this is our pivot point. And remember, k is over here. And so if k is over here, we know for sure this is in the right location, but this could be in whatever order and this can be in whatever order. But since k is to the right of the pivot, now this is the part we care about, and this is the part we can delete. So now we have 3 and 4. And our left and right pointer is just going to be pointing to that. So this is our left, and this is our right. Okay. Now we'll pick a random pivot. Let's just pick the last one for, easier time, I guess. And so now our array actually looks like we have a 1 and a 2 over here that we don't care about. We have a 3 and a 4, and then we have a 5 and a 6 over here that we don't care about. And the number we do care about is this, so we want this to be sorted. But anyway, let's just say we pick this as the pivot just to make it easier for ourselves. Obviously, we're going to randomize it in the actual algorithm. So we're writing from here, and we're writing to here. Is 3 less than 4? Yes, it is. So we're going to update both of them, because essentially we're going to swap the 3 with the 3. Now this is going to go over here. Now we are done writing everything, right? Because we're only looking for numbers that are less than the 4. So now that we're done, now we have to put the 4 where the right 2 is, and the right 2 is here. So essentially we're going to swap the 4 with a 4. And now we know this 4 is in the right place for sure, right? Like this, there might be a bunch of elements here, we don't know that, but this 4 is in the right place. And this was our actually k index that we cared about. So now this is going to be the value we're returning. We're going to be returning 4, and that would be the third highest number if this was sorted. That's kind of how the quick select works, and essentially let's go through it one more time just to like, not the whole thing, but let's go through the time complexity. So essentially you have some numbers, and you pick a pivot point, and on average, the way it's going to be is after all your stuff is sorted, your pivot's going to be somewhere in the middle, right? But worst case, if this was sorted, like let's say you do have a sorted array, let's just say you always pick the last number. Well, if you think about it, if you always pick the last number, and let's say your k is like the first number, like let's say k equals 0, or whatever the last number is, I guess k is like 6. And if our array was like 10,000, k would be 10,000. Now, in this algorithm, essentially what would happen is you would always write to the same index you're at, and then you would just get rid of like this last part, and then you'd always care about this last thing, and then your pivot would be here, you'd get rid of... So you're getting rid of one index in an O of n operation, so that's going to be basically n squared time. Or that's going to be n squared time. So our time complexity here is going to be, on average... And, oh yeah, so this is the worst case. So worst case, it's O of n squared. Now let's look at like an average case. So on average case, let's say we're always in the middle, right? Let's just say roughly, anyway. So if we're always in the middle, we're essentially deleting half of the array every time, right? So we're deleting half, then we're deleting half, then we're deleting half, and we're deleting half. And so if you think about it, that would be O of n plus O of 1/2 n plus O of 1/4 n, and so on up until it was 1. And so this simplifies down to O of 2n, which would be O of n. So if on average your pivot was somewhere around the middle, then this is an O of n time complexity. And space complexity is either O of n if you made a new array, or if you wrote over it in place, it would be O of 1. So either one. You could ask your interviewer for that, like, can I write over this in place or not? But yeah, I think the quick select is leaning towards... I think once you get how to do it, it's not super hard. Like, it's like a quick sort. I would say it's like a hard or medium, maybe. Like, it's easily something you can see and implement right away. It is super rare for, like, interviews, but just wanted to show that because just using a heap, I think, is, like, a little bit straightforward for this. Okay, so here's our code, and let's take a look at all of these. So the first one is we are just heapifying every single number. And so we're heapifying every single number, and the way I did it was I made everything negative, and then you just keep popping until you hit the k number, right? So if you have something like 1, 2, 3, 4, 5, 6, you would essentially have a heap like this. Obviously, I guess it would be, I can't really show you the order, but essentially I'll show you what it looks like when you're popping. So 5, 6, 4. And so essentially here you would pop twice. So the first number you'd pop is the smallest number, so you'd pop off this one, and then you would pop off this one, and you would store that in your result. So your result would be -5, and then you would return -5, which would be 5. And so we can run that. And it does work. But you can see the memory is not great because we are storing everything in a heap. Okay. So then we have the k-length min heap, where we are doing the same kind of thing, except now we have, so if our numbers were 3, 2, 1, 5, 6, 4, now we are just going through the numbers, and essentially we start out with a min heap of nothing, and we keep adding numbers, so we would add numbers up until our k length is reached, and now for every single number we check, is it greater than our minimum number, and if it is, then we do a pop and replace it with that number. So essentially in this, we would do a pop because 5 is bigger than 1, so we'd replace the 1 with a 5. And then for the 6, our min is a 2, so we'd replace the 2 with a 6. And then for the 4, our min is a 3, so we'd have something like this. And then, so actually our heap is length 2 here, so sorry about that. Our heap is actually length 2, so it would actually be like this. And then we would, so 1 we would skip, 5 is greater than 2, 6 is greater than 3, and 4 is less than 5, so we didn't do anything there. So we'd have these two numbers. And then, yeah, I think in this, yeah, I explained that one correctly. But yeah, here our heap is length 2, so we're guaranteed to have the 2 biggest numbers, and then our minimum of the heap is always going to be the kth largest number. So we can try running that as well. And you can see it should be a little bit more efficient space-wise, and it is. And then finally, we have the quick select. And so for the quick select, you have the left and the right, just like I described. They start off at the whole array. You have the res index, which is where your kth number would be in a sorted array, right? So for 2, it would be over here if this array was sorted. And then you get a random index, like I suggested, because you don't want to just pick the last index just because your array is sorted. It's going to be really bad. You get the value, and then you swap. So like, let's say you pick just this random index. You would swap it with the last number just to make it easier on yourself, because you don't want to be like checking after it. So we're going to swap it. We're going to write to the left. And then essentially every time we're saying if our number is less than the left, we're going to write to that index, and we're going to update our right index just like I showed in the picture earlier. And then finally, once we're done with everything, we need to swap the value in the right to index with the pivot, because that value in the right to index is going to be greater than the pivot, and we want our stuff to look like smaller numbers, and then the pivot value, and then bigger numbers. And so this would technically be like bigger would be a bunch of numbers, maybe smaller would be a bunch of numbers, and then pivot. So this part is sorted, but smaller is not necessarily sorted, and bigger is not necessarily sorted. Now let's take a look for that. Okay, so you can see it's pretty efficient, and this honestly depends on like the tests you run. So sometimes it's good, sometimes it's not. But yeah, so after you do that, remember we have our 3 cases where if the k index is our pivot, then we're done. If the k index is less than our pivot, then we're deleting the right side. And if the k index is greater than our pivot, then we are deleting the left side. And then finally, I just have a -1, but this should never actually happen. Okay, so that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.